Welcome to the Cosmic Savannah with Dr Daniel Kadama
and Dr Jacinta Delhaize. Each episode, we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Welcome to episode 56, where we have some exciting news.
Hi everyone. Yeah, sorry, this episode's been slightly delayed by COVID, as many things are these days. So I'm sure you'll forgive us, but yeah, sorry about that. But in the meantime, of course, there has been some extremely exciting news, which I'm sure many of you have already heard about. Of course, the Event Horizon Telescope put out a new press release. So you may remember in 2019, the EHT telescope took its first picture of a supermassive black hole. That was M87 star, and that's a supermassive black hole at a galaxy sort of outside of our own galaxy, a different galaxy. And then when Dan and I heard that there was going to be another announcement from the EHT, Dan was like, oh, it might be Sagittarius A star. Sag A star.
So yeah, we are joined by Dr Iniyan Natarajan, who is a postdoctoral fellow at the University of Witwatersrand in Johannesburg. And he'll be telling us a little bit about the discovery, his involvement, and some exciting news in terms of Africa's involvement going forward. But first up, I think we should just chat a little bit about the discovery, without taking too much away from Inyan. Super cool. I mean, the second black hole we've imaged. First one, M87 star, as you mentioned. And now we've got a nice selfie, I guess, of our own black hole.
Yes, just so cool. Like, it's so exciting. For years we've been telling people, yeah, no, there is really a supermassive black hole at the center of the Milky Way. We know it's there. We've seen indirect evidence of this by other stars kind of orbiting around nothingness, something that looks blank. And, you know, studying those orbits, we know that it has to be of a certain mass, and the fact that we don't see it means it has to be a supermassive black hole based on the mass. But it's very, very, very hard to make an actual image of it. Inyan will go into detail about why that is. But yeah, I guess examples online have said it's kind of like taking a picture of a toddler that keeps moving really, really fast. So it's very difficult to...
I think it's even worse than that. It was something like, we should look this
in the
up,
dark.
It was something like, you know, taking a photo of a penny in New York from London or something. It's insanely high resolution, and they do this in very incredible ways, using interferometry, using telescopes on either side of the world. And Inyan will be able to explain that too. We keep referring to M87 star and Sagittarius A star, but it's actually a black hole. Jacinta, do you care to explain why we keep doing that?
Oh, I mean, it's just the nomenclature, it's just the symbols that we use in astronomy to represent these things. So pretty much all galaxies have supermassive black holes at their center. We don't really know why yet. And that supermassive black hole, it has the name of the galaxy, and then it has a little asterisk next to it. When we say it out loud, we say star. So the supermassive black hole at the center of the galaxy M87 is M87 star. So then within the Milky Way, it's a slightly different naming. Dan, do you want to explain that part?
Yeah, so it's called Sagittarius because it's in the constellation Sagittarius, and then the A is actually refers to the region it's in. So you would have seen the meerkat image some years ago of the area around our black hole in the radio, which was a very cool image from meerkat. And that area is called Sagittarius A. It's kind of this complex radio source. There's all sorts of stuff going on. When it was discovered, it was obviously, you know, in the Sagittarius constellation, and it became known as Sagittarius A. And then you add the star, the asterisk, which refers to the black hole within that region.
Yep, exactly. And then we're lazy, so instead of saying Sagittarius A star, we say Sag A star.
We're trying to save time.
Yep. Save time, more astrophysics.
Save characters on Twitter.
Yeah, it's probably due to Twitter, actually. All right, shall we let Inyan explain the rest?
Absolutely.
All right, let's hear from Inyan.
Today we're joined by Dr. Inyan Natarajan, and he is a postdoctoral fellow at the University of Witwatersrand in Johannesburg, South Africa. Inyan, welcome to the Cosmic Savannah.
Thanks, Daniel and Jacinta. Yeah, I listened to quite a few episodes of the podcast, and yeah, I'm happy to be on the show.
Thank you very much for joining us, Inyan. We're very excited to have you today to talk about some very exciting new work. But before we get into all of that, can you just quickly tell us who you are and where you're from and what you do?
Yeah, so I am originally from India. I did my undergraduate in computer science and engineering, and I moved to Cape Town for doing my master's in astronomy at the University of Cape Town. And then I continued on with a PhD at UCT, and which focused on radio astronomy and techniques for analyzing radio interferometric data. So I'm generally working more on the technical programming side of things, algorithm development and that kind of stuff. And then I did a postdoc at Rhodes University, and now I'm a postdoc at Wits University. And I also work closely with the radio astronomy research group at Sarajevo.
Excellent. So, as Jacinta mentioned, there's some very exciting news which came out just last week, where the Event Horizon Telescope revealed the image of another black hole, the second from the Event Horizon Telescope, and this time our very own black hole at the center of our Milky Way galaxy, which is called Sagittarius A star. Could you tell us a little bit about that and why it's so exciting?
Yeah, so the collaboration recently released the first black hole images of the supermassive black hole at the center of our own galaxy. And these data were collected in 2017, along with the other black hole image that was released 2 years ago. And the black hole at the center of our galaxy is something that we are looking at like straight through the galaxy, and that makes it more difficult to image. And also, it's a much smaller black hole than the other one that was imaged in 2019, which also means it's rotating faster, which means you needed to develop new algorithms and new software to actually be able to handle that. And which is why it took almost 5 years since the collection of the data to come out with this image in 2022. And it's exciting because it's our own black hole at the center of the galaxy that we live in.
So exciting. I'm just like bursting at the seams over this. Dan and I were both messaging us during the press release being like, oh, is this humanity's final moments of not knowing what our local supermassive black hole looks like? But Inyan, let's take it back a step for our listeners. What exactly is a black hole, and what is special about a supermassive black hole?
Yeah, so a black hole is the point in space-time where even light cannot escape. The escape velocity that's needed to escape the gravitational pull of the black hole is so high that not even light or anything traveling at the speed of light can get out of the influence of the black hole. And this point of no return is called the event horizon, which is why the telescope is named the Event Horizon Telescope. And these are like some of the weirdest, like strangest and most high energy phenomena in the universe. And there are different types of black holes, or black holes can form in different ways. The one that people probably more commonly hear of is the stellar mass black hole, where a star that's more than about 30 times the mass of the sun, when it dies, it invariably turns into a black hole, which is much smaller than what we call supermassive black holes, which are giant black holes that are found at the centers of galaxies. And at this point, we believe that every galaxy hosts a supermassive black hole at its center.
So how big is our supermassive black hole? You said it's a lot smaller than the one in M87, but how small is small and how big is big?
Oh, yeah. The black hole at the center of M87 is really a giant black hole. Like its mass is like 6.5 billion times that of the sun. In comparison,
wow.
The mass of
6.5 billion?
Yes.
Wow.
It's crazy. It's really one of the largest black holes out there. And I think that the limit for like what you can call a supermassive black hole is 10 billion times the mass of the sun. There are a class that's proposed called like ultra massive black holes. Because I think we are really running short of superlatives here. But but yeah, so the M87 black hole is something that's really large. In comparison, the black hole at the center of our galaxy is more common, and it's only about 4 million times the mass of the sun. Only, when I say.
Only.
That's still pretty
only
big,
a cheeky
right?
4 million.
So you mentioned that to create an image of our black hole, the Sagittarius A star at the center of the Milky Way, was somewhat harder than creating the image of M87. The data was taken at the same time, and it took 2 years to get the image of M87. And M87 is a lot further away from us. It's in another galaxy. Is that because of the size?
No. In fact, Sagittarius star appears slightly larger in our sky than M87 star. But the difference is that M87 is a different galaxy, and you're kind of looking at a different galaxy away from our galactic plane, where most of the stars and the gas and the dust in our galaxy is located. You're not looking through all this interstellar gas and dust when you try to image the M87 black hole. That's one of the reasons. And the other reason was that the black hole in M87 is a much larger black hole because it's far bigger than the entire solar system. In comparison, the Sagittarius star it's probably about the size of Mercury's orbit from the sun. So it's far bigger, but it's much farther away, so it appears slightly smaller in the sky than the Sagittarius star black hole. But because it's far bigger, it also rotates slowly. During the entire duration of the observation, the black hole doesn't change in appearance much. In contrast, Sagittarius star, being a smaller black hole, rotates at a much faster rate. In fact, while this rotation rate is expected to be on the order of days to a month for M87, for Sagittarius star, it's on the order of minutes. So the appearance of Sagittarius star also changes. It's what we call variability. So that and the fact that we have to look through all the gas and dust in our own galaxy made it harder to analyze this data. And that's why we had to come up with new methods of calibrating, imaging, and modeling the data and extracting science from that.
All right, so it's really hard, is the moral of the story.
So how do we observe these? So you mentioned that not even light can escape from a black hole. We're looking at the event horizon of the black hole. What are we looking at, and how do we photograph it?
So what we see is a bright ring and a central depression in brightness, basically like a darker region within the ring. And this comes about because the central part, which is also called the shadow, is basically our line of sight into the black hole. Basically, that's where there's no light escapes from that part. But we are lucky in that these supermassive black holes are generally surrounded by hot gas and swirling plasma that's going on around it, that it's kind of accreting due to its gravitational pull from its environment. And this gas can radiate. And this light, when it approaches the black hole at a certain angle, will just fall into the event horizon and be lost to us forever. But at certain angles, this light, instead of falling into the black hole, can go around the black hole and come towards us. And this kind of happens to light that approaches the black hole from all directions. And this light gets warped around the black hole due to the space-time warping, and which is why all around the black hole you see this ring of fire.
And how come there's clumps in the picture? We've all seen the picture now of M87 star and Sagittarius A star, and they look fairly similar, but not quite the same. But both of them have these kind of clumps of bright patches. What are they?
Oh, yes. This is something that people probably do not expect to see because of what we saw in Interstellar. For example, there it appears more like Saturn.
That's exactly what I was thinking of.
So in the movie, the black hole appears more like Saturn, and the rings are very clearly outlined, and there are no clumps, or there are no brighter and darker regions relatively on the ring. This is due to a Doppler effect, basically, which is something that we study in high school physics. So basically, the light coming towards us will appear brighter than the light that's going away from us, and that's basically what causes these changes in how we perceive the ring to be. For example, there's more variability in the Sagittarius star image than what we saw from M87. So you'll probably see clumps, or what you can call hotspots, in different regions of the ring in both M87 and Sagittarius star. And in Sagittarius star, because it's rotating at a much faster rate, so during the entire duration of the observation, the black hole's appearance keeps changing. So basically, of the thousands, tens of thousands of images that were made, basically all these images were algorithmically classified into different clusters based on how the ring morphology shows up. And that's why you see this clumps of matter, maybe at slightly different areas on the ring, where more than 95% of the images show a ring-like structure. And the one big image that we all saw is an average of all those images.
Okay, so we're averaging images from different telescopes, and that's what the Event Horizon Telescope is. Could you just explain to us how the Event Horizon Telescope works and how it gets these images?
Yeah, so the Event Horizon Telescope is a global network of telescopes that operates telescopes or observatories that are located far and wide around the world to generate the equivalent of a telescope that's the size of the Earth. And this is done by a technique called interferometry, which ultimately, again, it's something that we all study in high school physics. It uses the principle of interference of waves in a clever way to combine signals from telescopes that are located at different locations on Earth. When these signals are combined in a certain mathematical way, it is as if we are collecting these signals from an Earth-sized telescope, but with a lot of holes in the telescope dish itself. And that's what makes radio astronomy and imaging in radio astronomy much harder.
So we want to fill those holes, right?
Yeah, this technique is called very long baseline interferometry. Basically, the baseline is the distance between these different telescopes or observatories that constitute the array. And as these baselines become longer and longer, again, you know how astronomers are with these superlatives. We just call them very long baseline interferometry.
Okay, so we have essentially a telescope that's the size of the Earth, as you say, but thankfully holes in it so that it doesn't completely block the sun. And it's made this amazing image of the supermassive black hole at the center of our galaxy. We see rings, we see these clumps, and this is, of course, work that's been done by an enormous collaboration of many, many different astronomers around the world. And you're part of that collaboration, is that correct? And what was your involvement in this project? What was your part in this?
So the collaboration consists of 350 scientists located around the world on 5 different continents. So my involvement in this was as someone who has worked on algorithm development for imaging, calibration, and simulation of astronomical data. And my involvement has been in those areas. So one of the things that I've been involved in is to write a simulation software along with Roger Dean to basically simulate how a black hole would look to a telescope like the EHT or to any very long baseline interferometer. So basically this software has to take into account of all the different atmospheric effects and all the characteristics of the instrument or the different dishes that constitute this array. And so basically you put all this information and also theoretical models of how you think the source should look like, and geometrical models that you can kind of create with basic geometry. So basically this software takes in a lot of information about the target of observation and information about the Earth's atmosphere and information about how your telescope works and the characteristics of the telescope, and it spits out data and images of how a certain source that's given by the theoretical simulation would look through a telescope like this. And this has been used to create a lot of simulations for within the collaboration for a lot of different studies, including this one. That's one of the things. And the other thing that I was involved in was to work on basically characterizing a bunch of morphological properties of the different rings in all these thousands of images that were created. So there are different imaging pipelines, or basically different imaging software packages, each of which created thousands and thousands of images from this data. So if you remember back when I said our telescope has a lot of holes, the measurements that could have been made from those regions which are holes could be anything. So basically there are an infinite number of possibilities that exist. But based on how we know, or based on the physics that we know, based on how we know black holes work, and based on other observations like past observations and observations in other wavelengths, we can kind of put some constraints on what the measurements in these regions should be. And so basically you end up with thousands of different realizations of these black hole images, none of which can claim superiority over the other. While image number 3 is as equally plausible as image number, 5065, something like that. So I worked on writing some software pipelines, which also involved a host of different software packages which are all used to characterize the morphology of the ring. Basically different parameters like the diameter of the ring and the width of the ring and the location at which the hotspot located on the ring. So basically all these parameters we kind of extract from each of these images. And then we also classify these images based on how much they look like a ring or how much of a certain kind of ring they look like. So I was also involved in that kind of analysis and software development for this project.
Awesome. And we should point out, I don't think we mentioned it, that, these are radio telescopes, the Event Horizon Telescope, but they work in a slightly different wavelength to Meerkat, which we talk about quite regularly. They work in the millimeter wavelength. And Africa is hopefully going to be joining the Event Horizon Telescope in the coming years with the African Millimeter Telescope. Can you tell us a little bit about that? It sounds very exciting.
Yeah, so we would really love to be part of the Event Horizon Telescope network. This will actually be mutually beneficial to the African astronomy community and also to the Event Horizon Telescope collaboration. For example, one of the primary targets of the EHT is Sagittarius star, which is located in the southern hemisphere. So the EHT can do with all the telescopes they can get in the southern hemisphere. So having a telescope in Namibia, like the African Millimeter Telescope, would greatly benefit the EHT. And if you think of the different telescopes or stations involved in interferometry as each shaking hands with each other, just the addition of one more telescope basically introduces a number of baselines. And that increases the amount of data that we have from any observation, and then that improves the physical constraints that we can put on the ultimate science that we can get from this. And we also hope that at some point we can also have a station in South Africa, which could also provide much needed short baselines. So if we have a station in South Africa and have a station in Namibia, then it becomes easier to constrain the characteristics of the antennas, which are very important in how they behave during an observation. So these are called short baselines, as opposed to the baselines that you can form between a telescope in South Africa and a telescope in Chile, for example. And these help us constrain the properties of the instrument itself better. So this will be a massive boost to the Sagittarius star campaign in the EHT, and also it will really work in synergy with our other projects like Meerkat and other high-energy astrophysics projects or multi-wavelength projects that are being pursued in Southern Africa.
That's so exciting. And this might be a novice question, but will the SKA be able to be part of the EHT eventually when it's built, or does it operate at a completely different frequency?
Well, the SKA does operate at a much lower frequency, or at a much higher wavelength, as we would say.
Okay, so probably not part of the EHT itself, but probably we'll be able to do some sort of VLBI with the SKA, but just not at these wavelengths.
Yeah, exactly. There are plans for SKA VLBI, and we can definitely observe the center of our galaxy, but we'll be observing at a much different wavelength, which is also always necessary. It always gives us a complementary picture of what's going on.
I guess we won't be able to see Sagittarius A star, though, at those longer wavelengths, because there's other stuff intervening our line of sight that will, be glowing at these radio wavelengths, and so blocking our view of the center. Yeah.
Sagittarius star itself would be invisible to us because it'll be opaque at those wavelengths.
Right.
What is next for the EHT? We've got our picture of M87, which is, I think, the nearest galaxy. We've got our picture of Sag-A star. I assume we're working on improving those images. But if you're able to tell us, what's next?
So this is kind of the very beginning of EHT imaging. So on the instrumental side, there are efforts for something called the Next Generation Event Horizon Telescope, which aims to add a lot of different stations to the existing EHT array, which will, of course, greatly improve our ability to image these black holes. And there are also maybe longer term plans for putting some radio telescopes in space and doing interferometry with much larger baselines. But it comes with its own complications. Basically, your stations are moving relative to the Earth, so it's just even more complicated than that. But as far as the observations and the science are concerned, the image that was released recently is just the Stokes eye image, what we call the total intensity image. And there are still polarimetric studies to be done and polarimetric images to be made with the Sagittarius star data. And so in a similar way to the images that were released in 2021 with M87. Also, EHT has collected data in 2018 and also again in 2021 and 2022 with a few new stations in the mix. So we also expect the analysis of this data to greatly improve on what we have now.
I just want the listeners to understand that this is extraordinarily difficult stuff that's going on. So it takes years to analyze the data and try to get an actual image and get some science results out of it. So what you and the whole team, Inyan, have done is really remarkable. And so I think what you are saying is that we've seen the images of Sagittarius A star, M87 star in total intensity, meaning just collecting all of the light that we can coming from there. But then we want to look at the polarization, meaning light can be polarized in different directions and you can split up that light, and you want to look at the black hole in light that's polarized in one direction versus light that's polarized in a different direction. What can we learn about an object if we look at the polarized light? And you mentioned that we have seen polarized images from M87. I think I might have even missed that. What did that look like?
Oh, yes. So those results came out in 2021. I mean, obviously not in like big press conference like this, but I think it was about a year ago that released the polarimetric image of M87. So basically, when you look at these images in polarized light, you get an idea of the characteristics of the magnetic field that exists in the region around the black hole. So you can get the direction of polarization of light, which tells us how the magnetic fields are organized, or like how strong they are, and how much they can affect the accretion of matter around the black hole. And this is exactly what we hope to do with Sag-A-Star data, which we hope will help us improve our constraints on the accretion rate, or like the strength of the magnetic fields around the black hole, and like the structure of the magnetic fields around these black holes.
Right, so this is going to help us to understand magnetic fields.
Yes, yeah.
Maybe answer that question that one annoying person always asks in a conference: have you considered the effect of magnetic fields?
That is so true.
I mean, the magnetic fields around a black hole must be nuts. So.
Yeah, they must be doing crazy things. Thank you, Inyan. Just one more question from me, and then I don't know if Dan has more questions, but I've just thought of a whole bunch. What did it actually feel like to you when you first saw the picture that we saw in the press release recently, and how did it feel when it was released to the world after so much work?
It was so different, like between M87 and Sag-A-Star. During the M87 press release, I was actually with my family back in India. So we were watching the press conference live. I was like with my mom and dad, and I was like getting all excited and like trying to explain stuff to them, and like well, I don't know how successful I was, but at least the general excitement kind of like caught on to them. But it was an incredible feeling. Like, I mean, I was like a much newer member in the collaboration when the M87 release results came out. So it was just like such an exciting feeling. And I just wanted to be more of a part of these things. I mean, you work hard, you work a lot, you work for a long time, like for years and years. And then suddenly you see something like this, like, you know, like terabytes of data, like everything compressed into like, I don't know, like 100 KB image. And but it's worth it. It's well worth it, and I have been able to become like a bigger part of. At least I've been able to do more tasks within the Sag-A-Star project, and I'm hoping to be involved in these things further in the future as well.
Inyan, thanks so much for sharing your excitement with us, and I think you did an excellent job of explaining to us. I'm sure you did to your parents too.
Oh no, they were also like so happy.
Is there anything you'd like to share with our listeners before we go?
Yeah, I just want to thank you guys. It's been a really great chat. Like talking about these things with you. 2 years working from home, you do want to like just chat with friends about astronomy stuff as well in a relaxed setting.
Well, it's been an absolute pleasure for us.
So great. Thank you so much, Inyan, and good luck with the rest of your work.
Thanks. You too. Thanks for inviting me.
Oh, that was awesome. Just, so exciting. We now know what our black hole looks like.
Yeah, it's super cool. I think, everyone was over the moon in 2019. We didn't really know what a black hole or the area around a black hole was going to look like. This is very similar, I guess, with some slight changes, and obviously a much smaller and harder to image object, as Inyan explained. But super cool to have our own galaxy's black hole now. We've got a little nice postcard image of it. And yeah, I think that the other cool thing, which, if you haven't seen the M87 image, then you're in the minority of the global population, because I think that the number was 4.5 billion people saw that image, which has got to be the biggest, astronomical event or news event ever.
Yeah, it's massive. It's the Eye of Sauron kind of looking image if you haven't seen it. But that's kind of what it looks like. I'm just going to Google now M87 polarized image because I want to know what Inyan was talking about.
Yeah.
Polarized
tap,
image.
tap.
Wow. Oh, cool.
It looks fake. Hey?
It does look fake. Is this real?
I
think it is real.
No, it is, yeah. Oh, cool. So you can see like the magnetic field's all spiraling in.
Yeah.
There's some weird stuff going on the left there.
Yeah, we'll put it on the blog as well. But Google it yourself and have a look. It's like the glowing ring, like the Eye of Sauron thing. But then it's got these, like,
the Eye of Sauron again.
curved stripy things around it. It's like eyelashes kind of thing inside the eye. It's cool. It's really cool. So that tells us about the magnetic fields.
I don't know if as many people as that have seen Interstellar, probably not. But the image in Interstellar, which Inyan referred to too, was also cool. And that was a simulation. And at the time, I think it was one of the better simulations, if not the best simulation of the area around a black hole, because movies have budgets that astronomers don't. So
far exceed our measly budgets.
So yeah, I mean, I think that if you have a look at Interstellar's black hole, it's actually a very, very realistic simulation too.
Yeah, and the astrophysics on that movie is really quite accurate, because Nobel Prize winner Kip Thorne consulted on that movie, except at the point from which they fall into the black hole. Sorry for that spoiler alert, but should have said that first. Spoiler alert. But from then on, it's purely Hollywood physics, because things fall apart pretty quickly from there.
I don't know what the statute of limitations on movie spoilers is, but I feel like Interstellar's been around long enough. Okay, great. Very exciting stuff coming up, and I think that it's awesome that Africa's going to be getting involved soon. The AMT is coming, and that'll add, as Inyan said, various baselines. So it'll add more than just one telescope. It adds a whole lot of baselines, which means we're getting much more accurate images. And the EHT telescope is not done. There's going to be continuous improvements, and I'm sure they've got some awesome new surprises for us coming up, which they're not allowed to leak. There's a huge amount of secrecy around the EHT.
I know.
I know there was for the first one, but I feel like everyone kind of knew this was going to be Sag A-star, but still, I guess it's just for the media. They do a really good job of it.
Yeah. Well, I think it's great, because I didn't know about it either, and neither did you, I think, and it was a nice surprise.
Yeah. All right. So I think that's it for today.
Yeah. I guess before we wrap up, we do our usual tradition.
Oh, right, yeah, of
How
course,
are you, Dan? How are you? You sound slightly nasally. Are you all right?
Yes, yeah.
You had a cold?
I have had something of a cold, just in my nose, and yeah, it's probably a good thing we delayed for a week so that I sound even less nasally than I did last week. Otherwise, I'm good. I feel like it's the end of the year already. I feel like I've burned up all my energy for the year, but we're only in May. So, but otherwise, I can't complain too much. How are you?
Yeah, I'm doing really well. Got lots of exciting science going on, which I'll be able to talk about eventually. But the big thing is that this weekend on Saturday, I'm giving a TED Talk, TEDx, in my hometown, which is going to be really exciting. Dan, you've actually given a TED Talk, so I think we should link to your talk somewhere on our website, because it was really great. It was about kind of ethnoastronomy, cultural astronomy in South Africa. And well, after my talk, I'll be able to explain a bit more about the topic of mine, but I'm really looking forward to it. I've been practicing really hard. Dress rehearsal is tomorrow. Bought new boots for it, which I can't wait to wear.
I mean, I hope the camera takes in your boots and doesn't just focus on the top half of you then.
Well, I better.
Otherwise, we can post a picture of the boots on the website too.
Yeah, we should. And other than that, yeah, still at home in Australia, hanging out with my dog. If you follow me on Instagram, you'll see lots of pictures and videos of the dogs, and also the birds that we live on a bushland property. Lots lots of birds around.
Yes, I see you've been taming magpies.
Yes, yeah, we have these magpies and all of these other different types of birds that come to get fed whenever we feed our dog outside. And now I'm teaching them tricks. They jump for their food. One of the magpies takes food out of my hand.
I'm sure you're not supposed to feed the wildlife, Jacinta.
I mean, true, but we have lived here for about 20 years and they've decided they tamed us, not the other way around. They trained us. So, well, we've learnt what we are and aren't allowed to feed them, so I think the birds will be okay. Yeah. Alrighty. Okay. I think we can wrap it up there.
Well, good luck for your talk on Saturday, and
Thank you.
I hope that we are able to watch it all soon. Judging by my TEDx talk, it took a couple of months for the TEDx to approve it and kind of edit it down and everything. So hopefully we'll be able to see that sooner rather than later. But yeah, I think we should wrap it up there. Thanks again for listening. We hope you'll join us again next time on the Cosmic Savannah.
You can visit our website, thecosmicsavannah.com, where we'll have the transcript, links, pictures, and other stuff related to today's episode.
You can follow us on social media, Twitter, Facebook, and Instagram at Cosmic Savannah. That's Savannah spelled Savannah. You can also now find us on YouTube, where audio-only episodes are uploaded with closed captions, which can be auto-translated into about 200 different languages, including Afrikaans, isiXhosa, and isiZulu.
Special thanks today to Dr Iniyan Natarajan for speaking with us.
Thanks to our social media manager, Sumari Hatting, and our audio editor, Jacob Fahn.
Also to Mark Olnut for music production, Michal Werchek for photography, Carl Jones for astrophotography, Susie Karras for graphic design, and Justine Crook-Manzour and Moloko Makweja for transcription.
We gratefully acknowledge support from the South African National Research Foundation, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, and the University of Cape Town Astronomy Department.
And we'd really appreciate it if you could rate and review us and recommend us to a friend.
And we'll speak to you next time on the Cosmic Savannah.
Episode 56, Dan and Jacinta, Commencing Silence. I forgot your name there briefly. I was like, is it Dan? It is Dan. I don't know what's happening to me today.
I feel like we've really grown apart since you moved in.
No, it's not true. All right, serious face. Let's go.